Hey everyone, today we're going to talk about sets. Now, a set, loosely speaking, is a collection of stuff. And there's really not a whole lot more to sets than that. This very simple seeming definition kind of captures all there is to know about them. For example, if we take the numbers 1, 3, and 5 and form a collection with them, that is a set, which we indicate using these curly braces. And separating each thing in the set, or element of the set, with a comma. Now, because everything that kind of fits this collection of stuff definition is a set, there's a lot of flexibility on what can't be a set. For example, you don't have to have numbers in your set. You could have colors, for example, red, orange, blue. That's a set. There's no rules on what can or can't be in a set with other things in it. So you could have one pineapple and square together in a set. That'd be a valid set. There's no rules on how many things you can have in your set. You can even, for example, have an infinite number of things. You have 1, 2, 3, and so on. All the positive whole numbers. That's a set. Set's even got a special name, as we'll see later. You can put other sets inside sets. So you could have the set containing James and Nayla. And I don't know, the two-dimensional points 4, 5. That's a valid set. You can even have nothing in your set, right? You can have an empty set. This is also, besides the empty set, also called the null set. And often written in shorthand using this symbol, a circle with a line through it. One thing to talk about is that we don't really have this notion of things being in a set more than once. So for example, something like this, 1, 2, 2 again, and 4. That's not really a meaningful concept as we're going to be talking about sets. We're not really going to consider this as being part of the world of set theory. There are branches of mathematics where you would consider something like that, but we're not going to have to worry about any of it. For our purposes, something is either in a set or it's not. And that brings me to my next point, because talking about being in or not being in a set is kind of the most important thing you can do when you're working with sets. For example, the number 1 is contained in the set containing 1, 3, and 5 that we looked at before. Whereas the number 6 is not contained in that set. In 1, 3, 5. More formally, we might say that 1 is an element of this set. 1, 3, 5. Whereas 6 is not an element of that set. Namely, the set containing 1, 3, and 5. And all this is pretty self-explanatory, I should hope, because you can look inside the braces and see that 6 is not in there, whereas 1 is. So it's a little bit inconvenient to have such a kind of simple concept be such a mouthful to write out. So instead of these, we write 1 with this little e-looking symbol that means is contained in this set. And that really cuts down on a lot of writing when you're talking about sets. Similarly, we'd write 6 symbol with a little slash through it to mean it's not contained in the set. And once again, that cuts down on a lot of writing. So all 3 of these lines, one's contained in the set, one's an element of the set, and one, this little symbol, the set, all of these 3 mean the same thing. Now, this brings me to a few fine points that I often see students confuse. Firstly, that containment is different from equality. This is especially problematic when you see things like this. When you're looking at both 4, for example, and the set containing 4. Now, even though it might look like these are basically the same thing, they aren't. Because one of them is a set, and one of them is a number, and numbers are not sets. So it's not accurate to say that one equals the other. What you would say is that 4 is contained in the set containing 4. Which sounds like a bit of a meaningless sentence, but it's necessary. I also see some students getting confused when there are multiple layers of sets. So if we take that set from before, well, it's accurate to say that 1 is contained in this set because it's right here. It is not accurate to say that Mela is contained in this set because Mela is not actually in the set, right? The 3 things in this set are 1, the set containing James and Mela, and the ordered pair 4, 5. And Mela is none of those 3 things. Mela is not 1, Mela is not the set containing James and Mela, and Mela is not the ordered pair 4, 5, so Mela is not contained in the set, even though it might look like she is. And finally, I see lots of students confusing 0, the empty set, and the set containing 0, because all of these seem like they're talking about nothing, when in reality, none of these are equal. Like before, 0 is a number, and the empty set is a set, and numbers are not sets, so these 2 are not equal. And the empty set is also not equal to the set containing 0, because the empty set has nothing in it, and 0 is a thing. 0 is also not contained in the empty set, as some students seem to think, because, once again, the empty set has nothing in it, and 0 is a thing. So, just a couple of things that might be easy to miss when you're working with sets. Alright, for the last part of the video, just want to talk about a few sets that are seen commonly enough that there's agreed upon symbols to talk about them with. First one we've already talked about, the empty set. This, we've seen, is denoted using this symbol. Then there is the natural numbers, which is denoted using this n with a bar. So these are the natural numbers. This is the non-negative whole numbers. So 0, 1, 2, and so on. Now, I should note that this symbol means slightly different things depending on what context you're seeing it in. Some people, when they write this symbol, are talking about a set that doesn't have 0 in it. I've always interpreted it to mean the set that does have 0 in it, but it's always nice to confirm whenever you see it in a new context which one is being talked about, because it varies from place to place. Next up, we have the set called the integers, which is denoted using this z with a bar. So this is the integers. And these guys are all the whole numbers. So pretty much the natural numbers, but you also include the negative ones. So this has got 0, it's got -1 in it, it's got 1 in it, it's got 2 in it, it's got -2 in it, and so on, so on. Next up, we've got the irrational numbers, which are q with another bar. So the rational numbers. And these are all fractions of whole numbers. So one half would be a rational number. Next up, we've got the irrational numbers, which are q with another bar. So the rational numbers. And these are all fractions of whole numbers. So one half would be a rational number. And in this set, because 1 and 2 are whole numbers, so the fraction of them is a rational number. Every whole number is a rational number, so 7, for example, is equal to 7 divided by 1, and would be in the rational numbers. Every terminating and repeating decimal is a rational number, because all of those can be expressed as fractions. For example, 0.11 is equal to 11 over 100, so it would be a rational number. Something like 0.142857 repeating, that would be a rational number because it's equal to 1 over 7, which once again is a fraction of two whole numbers. But things like the square root of 2 and pi are not rational numbers. They're not contained in the set, because neither of those can be expressed as a fraction of whole numbers. To talk about these numbers, we're going to need a bigger set called the real numbers, denoted by this r with another bar through it. These are the real numbers. And this is the entire number line. So everything that was a rational number is in here. For example, 1/7 is a real number. It's in this set. All the whole numbers are real numbers. They're in this set. And those numbers that we couldn't include before, square root of 2, in the set. Pi, also in the set. And this is pretty much the biggest set of numbers you'll have to think about at this level. This set of real numbers kind of encompasses all we need to know. You'll also see the set of all points in the 2D plane talked about, and that's written as r squared. So the real number symbol with a 2 in the superscript. Once again, this is r squared and this is all 2D points. So things like, 1, 2, these are in R squared. 5, pi over 7, that's in R squared. But notably, a number like 5 is not in R squared, because 5 is not a point, and R squared contains all points in 2D space. Anyway, that's about all I had for you guys today. Hope you guys enjoyed the video, and see you all next time.